All right, today's video is covering Commodore 64 source code optimization so that you can fit a large program into a smaller space. And it's usually not something that's done until you're at the end of a project or after you've completed a section and you want to make it a little more tidy. In this example, I wanted to do a submission for the Cassette-50 charity competition that's going on right now over at itch.io. And what I thought I would do was use a couple of programs that I've already developed and covered on videos. The first was this maze program that draws a maze. And it's pretty basic. All it does is draw a random maze. And I thought there's got to be a way that I can somehow incorporate that into a game. I remember that I had a prior video where I covered the 4-player interface port, and I thought it'd be fun to try to make a game out of that, combining these two programs. So here we're using the joystick and port 2, and if I swap joysticks by pressing Alt-J, I control the other joystick, or the other player I should say. And this isn't really a game, it's just drawing a character on the screen. And then you can enable the user ports and control players 3 and 4. And then here's player 3. And so you get the idea. You can move 4 different players. These could all be moved around independently. And so that's how I came up with the idea for Amazing Race. And I later changed the idea from just the race to Amazing Quad Race because I came up with the idea of playing around with the colors to some sort of a change to the way the game's played, so that might throw you off as you're playing the game. And in Amazing Race, the whole idea behind it, and I'm going to show you one of the earlier builds. And so this was an earlier build, and I have the main program, the Maze program, which was taken from the earlier version, and then the 4-port adapter, which all this does, I took it directly off of the website, the Protovision website, I believe, which is the source code which shows you how to read the joystick ports. You initialize it once in your program, and then you do a joy read, and then you just read the values to determine which joystick is in use. And let's run that by hitting Control and F5. And so here's an early build, and at that time I still had it called Amazing Race, and I kind of liked this orange look, but that it's red when you actually look at it when the colors are properly displayed. And that's just a setting in here in the emulator. But one of the problems we had was control in the game, and that was later tackled at a later date. But you can see here, you can play through the maze, and if you can get to the end, see if I can get to that spot. And it's pretty close to what I have now, but I think it's a lot better at the end result. And then you just hit fire to start over. And of course, you could play all 4 players at the same time. Now, because I wanted to enter this into the Cassette-50 charity competition, I needed it to be able to fit under memory location address 1000. And right now I have it assembling at 1000, but I'm going to switch it to 800. And you can see just how far over it was. So at the end here, we're at 1417. So I need to shed off that 417. So 1417 minus 1000. So I'm 1047 bytes too large. So this was what brought me to the optimization video that I wanted to cover here. And one of the first and biggest optimizations that I could most easily make to the program, rather than going and changing the code itself very much, was to go in and take a look closely at what the variables that the program use are. And some of the biggest problems or the uses of memory are it has a stack, an X stack and a Y stack. Now there's not much we can do about these two variables because tracking the X position and the Y position. So it's not just setting a 0 or a 1, which if it was, there could be things that we could look at in order to optimize. But this other variable, this is the other variable that is using a lot of memory, is 512 bytes. And in this case, it is just setting values to 0 or 1, and it's tracking visits. So if it's already been visited or not, it's a yes or no field. And so what I did in order to try to optimize this program was I decided to share the address space at 400, which is the screen memory, with the maze while the maze was being drawn. And so what that does was it allowed me to combine or to change or to not have to use actual memory, program memory space in order to use this. I'm using the screen memory space. And you'll notice that in more current builds. Let's go to a more current build. When the maze displays, see all the exclamation points that we're displaying there? That is as a result of the shared memory with the screen. And all I did, so it did share that memory, but then I had to write a small program to swap out those characters. And I ended up calling that remove visits. And what it did was it looked for the weird characters and switched them back into a space or a wall character, depending upon which it was. And so yeah, when you look at it that way, even though I saved the 512 bytes, I had to write a program that took up some of that, gave some of that back. But overall, I ended up saving quite a bit of memory right there. Now I want to kind of jump into the rest of the memory saving techniques that I used, and then also some of the ways to extract more memory for use for your program. So over on the itch.io website, the Cassette-50 charity competition website, Shalon had posted some the rules and some tips and tricks. And he generously posted this little code snippet which shows you how you can use memory below address space 400. So using these tips, I was able to use some of the memory in this address space right here. And 143 bytes here, 131 bytes here, etc. And this allowed me to be able to squeeze or pack even more features into the program by using these little tips right here. Now, in order to get this to work, unfortunately, the CBM Program Studio would not cooperate when it came to using that address space. The program would crash every time. And I was unable to get assistance with that. And in order to actually keep going forward, I ended up converting my project to Kick Assembler and have been using the Sublime editor, just as I described in one of my prior videos. Basically using that setup, I'm using Sublime and the Kick Assembler, and it's pretty much verbatim how that video described it, as I was saying. Now what I did was I copied and pasted in Shalon's program code. I made a copy of it and kind of felt out what worked for me and what didn't work. And there were a few gaps in Shalon's code in terms of we found out later that even though he says you can use all the space could be used, there were a few places where some of that memory was being bashed when the program was loading in. And you find that out when your program crashes. So anyway, let's go into now that I have it over here in Kick Assembler, And let me compile it for you just to show you. This is the actual finished game that's loaded right now on itch.io. And it compiles in, hold on. And it's close, but the last address space it uses is FE1, and FFF being the max that it's allowed in the competition. And one of the tips that Shallon used, I'd like to share with you here, it doesn't have to do with optimization. It has to do with determining whether or not your program is using any other address space. So the rules of the competition say that you can't go above address 1000 unless it's for normal I/O like color and video or sprites and things like that. And he has some tips in this link here on how you can determine that, and I wanted to share that with you. So if I went in here and I were to do a hard reset and follow his tip here, go into monitor, activate the monitor, and type the command wexec F5DA and hit G to go. Then drop in your program. He says to drop in your program, and let's do that. Just kind of drag and drop it over there. And that first statement stops it before it actually starts executing your code. And then he wants you to type in this command right here, wstore 1000 to CFFF, wstore E00 to FFF, F, and hit go, and then run your program. Then if at any point your program, let's see, if at any point your program goes outside the bounds of those stored memory spaces, then he knows, it immediately knows that you are not following the rules or inadvertently not following the rules. And so I thought that was interesting. It's a really neat way, and it's also useful for debugging. So if you want to monitor a particular program space in bytes, you can just do a store between address 1 and address 2, wstore. And so any time a program attempts to write into that memory space, the program will break. And so that's what that does. Of course, when I brought it right over to Kick, and even after I used those memory saving techniques, I still had some work to do to get the program to fit under address space 1000. And that's what brings me to these tips. All right. So one of the most impactful things you can do in terms of optimization is to go through your variables and throw as many of them as you can into the zero page address space. And that's the space, the address space occupied by addresses 0 through 255. And the reason why that makes such a big difference is because when your program utilizes LDAs and STAs, increments, decrements, anything to do with zero page, it saves bytes for each command because zero page uses fewer bytes. So for example, in the absolute, comma X, absolute, comma Y, if you compare that, there's 3 bytes in use versus in the zero page for LDA, you're only using 2 bytes. So if you have a ton of LDAs and STAs and that sort of thing using your variables, you will save quite a bit of memory just by switching. Not even having to do any real optimization, just by switching and using zero page. So that's what I've done here. I've thrown a lot of the variables that I could into the zero page. And what I did was I created a label here for the beginning of zero page and the end of zero page. And then that brings me to my next tip for optimizing your program code. My next tip is if you are using an address block, it doesn't have to be 0 page, and you want to initialize all those variables, rather than doing something like I'm doing here, if the variables are 0, rather than, loading accumulator, storing it on that address, loading the accumulator, store it, you can kind of initialize an entire block by taking the beginning address of the block and the ending address of the block and put it in a loop. And here's the loop here, and it just initialize the whole block at once. And to me, it's a almost more of a efficiency thing, but it also can be an optimization thing that can shorten your program if you reduce or save bytes in doing it, and it does it quickly. Tip number 3, if you're doing an LDA and you want to compare it to 0, you don't need the CMP number 0 there, so you can actually comment that out. And you can just say branch if equal, and that implies branch if equal to 0. Basically saying if the 0 flag is set. And the same thing, you could also say branch if not equal to 0, but you don't need to explicitly put CMP number 0. So it's a very simple tip, and I know it seems like it's not a lot, but if you have several of those in your program and when you're writing code quickly, sometimes it just blurts out that way and you don't even realize it, and that's a place where you can optimize. If you have a situation like this where you're doing a JSR and then you have an RTS, it's a really simple tip. You can just change the JSR to a jump or a JMP and then comment out the RTS saves 1 byte. Really simple tip. It has saved me a few bytes here and there. Highly recommended. If you have a situation like this, where you have a branch if carry set to go to check fire, but you also have a JMP right after that. Now this won't work in all situations if you have a large jump, but what you can do is instead of doing a JMP, you can do a branch if carry clear to the same address space, and if that works, you save 1 byte. So that's a quick tip, optimization tip. Now, if the branch is too far, you might have to rearrange some code to see if you can fit it into the 127 bytes, the requirement. My next tip is if you have a loop where you're looping forward, like you're doing a INX or an INY, but then you're doing a comparison. If you reverse the loop and you load the X register with that value initially and then instead do a decrease X or decrease Y, that you can then eliminate the comparison at the bottom. So I can give an example. Let's bring up kick assembler. So here I've written a quick program that will draw the number 1 40 times across the top line of the screen. So you see that it has the number 1 going all the way across. Now what you can do to save 2 bytes in this example, you can load this with 40. Actually, you have to load it with 39. And you can actually eliminate this line right here. So if you load this with 39, change this from a branch if not equal to a branch if positive, or a branch plus. Also change your DEY, and that will save you 2 bytes. Now, if you left it as a branch if not equal, what happens then is as soon as it does the DEY, it detects that it's 0 and it returns off the loop, so it leaves you 1 character short. So in order to reverse the loop, in order for this particular tip to work, you have to switch it to a branch if plus. The problem with that is, yeah, the branch if plus and minus is checking the negative flag. So it will not work for values up here greater than 127. Because if the negative flag is set, then it will automatically exit this loop. Learned that one the hard way. The next tip is kind of staying in here in this example. If your program is doing something like an increment some address, and then it loads in that address, to branch somewhere, if it's doing something and it only needs to compare it to 0, well, the increment commands and the decrement commands set the 0 flag, so you don't need to load the value in. You could eliminate that load command and potentially saving 3 bytes. So that's a quick tip right there. And you can also, I believe they set the 0 flag and the negative flag is set. Yeah, so the negative flag and the 0 flag is set when you use INC and DEC. So that can potentially save you some bytes. My next tip is some of these might just seem like common sense to most people who write assembler code all the time, but I have the situation sometimes where I'm loading a 1 in and I'm storing it in a variable. And if you're only loading a 1 and you're storing it, and it's only going to be a value that's 0 or 1, well, instead of loading 1, if it's initialized to be 0, you can just do a INC on that variable instead of doing the LDA STA. And that could potentially save you 2 bytes right there. And then the next one's a little more tricky. So in this example, if you're really hard up for space and you see you have these JSRs here, I have one to draw the start characters and to draw the maze border. Well, that's nice to make it look good for readability, but if those subroutines are only being called once, you could embed them directly at the top right here rather than doing a jump sub, saving 3 bytes for each call. And as long as you have your code commented, you could copy this code right here, paste it in up at the top, and you save 3 bytes for each one that you do that with. This next tip that I have is a little more complicated, and it takes a little more analysis of your program code. But if you notice that you have a block or a chunk of code that's being repeated more than once, you can convert it into a subroutine like I did with this one here called optimize peak. And then you can jump sub it rather than having it in the code duplicated in multiple places like I had it at one point. And so that can end up saving you a lot of space depending upon how you do it. Oftentimes you can spot duplicated program code a lot easier by actually looking at the assembly dump, and CBM Program Studio actually has a really excellent program dump when it compiles. And so you can look for areas that might look the same, and you have to really look at it like this here and this here looks like it's exactly the same, but some things change in between, like this is a decrement versus this is an increment. And so you have to really kind of pick culprits for what would be the best way to save some bytes. And I use this method in order to find shared code. So if I saw a similar chunk of code that I could make a subroutine, I would make it a subroutine, or I would make a jump command to jump to that from one to the other so that it's not being duplicated twice. And I use that often to shrink the code. My final tip is not one that I ended up using in this particular source code, but was to use the bit command. And what the bit command does, it's very similar to a AND command, except that it doesn't change the value of the accumulator. So you can load the accumulator with a value, use a bit command to check what values are, similar to an AND command, and then it will set the zero flag, negative flag, and overflow flags, but it does not change the contents of the accumulator. Now, this is useful, can be used to actually save bytes. So in this web link, they list a pretty good example right here of how you can save 2 bytes in this particular example. You can use the bit command if it's embedded, the actual instruction code, what this code here, to save 2 bytes. So normally, in this example here, we're clearing the screen by calling this sub. Then we're going to print an exclamation point by JSRing to here, an asterisk, an asterisk, an asterisk, and then another exclamation point. Now, normally if you were to write this, you probably would do a JMP from here to this spot right here to output this. Well, you don't have to do that. So that's where you save 2 bytes, because how this program works is it turns this into a bit command, and then they stack together. So it's bit, bit, then JSR. And these bit commands don't change the accumulator. Since they don't change the accumulator, they're harmless, and then they just write out the character that you JSUbbed with. I know this is confusing. I know, believe me. But after you look at it for a while, kind of break it down, you realize what it's exactly doing. And I'll leave a link to this page here so you can properly mull it, mull it about in your brain. But it is more of a complicated example, and I don't actually use that in my program. I didn't have a need for that, but I could see where it could be useful, and it's a useful command to use. And it could save 2 bytes if you don't actually need to change the value of the accumulator to use the bit command. So there you have it. Those are my tips for how you can save program space. Now, combining all of those tips and doing all of those things will ultimately save you hundreds of bytes, if not thousands, if you do it right. Now, if you already naturally program that way, that efficiently, you're more like a robot than a human being, probably. But most people do have optimizations that can be made when they go back and look at their program code a second or a third time. And that was how I was able to compress all of the program space under address space 1000 and submit my entry for the Cassette-50 charity competition. I realize that sometimes optimizing for space can make your program a little bit slower sometimes. And conversely, optimizing for speed can make your program much larger. So it's just kind of the inverse. But in this video, we were just discussing optimizing for space. Anyway, thanks for watching. I hope you found it interesting, and I'll catch you on the next video.